thank you very much, Ray. Had a great day here and talking with students and with faculty, and hope I'll keep you interested this evening. I wanted to give you a sense of what I hope every chemist views as an imperative to start working on this problem. And that is basically, how do we transition ourselves off of fossil fuels in the future to, it's not going to be tomorrow, it's not going to be 10 years from now, but maybe a few decades from now. How do we get ourselves off of fossil fuels so that we can preserve the planet for future generations? And so, as Ray said, basically about a little over 2.5 years ago, I became the founding director of this new center at Princeton called the Almoner Center for Energy and the Environment. I'll have a little bit to say about that at the end. But without further ado, let me see if I can get us oriented. So how many of you have seen a slide like this before? Okay, so some of you have, but most of you haven't. So this is an interesting slide, and it's unfortunate. I don't know, can we dim the lights in the front at all a little bit? Is that possible? Or if, but if you can't, without making everybody go to sleep with the lights off. If it, because I know that at least the people in the back aren't going to be able to read this slide, so I want to lead you through a little bit of this. This is called an energy flow diagram. And the bottom, I don't want people to go to sleep, so maybe we should raise it back up a little bit. This? Anyway, okay, that's fine. So, so what you're seeing on the left is all of the inputs of energy. This is for the U.S. in 2011. This was put together by Lawrence Livermore National Lab. First time I saw one of these was in 2005, I think, and it's been interesting to see the evolution even in 6 years in terms of the energy inputs in the U.S. So these are energy inputs. See down here, the big green, dark green one is petroleum. Okay, and these are in quadrillion BTUs. Right now, the U.S. uses about 97 quadrillion BTUs. Among friends, that's 100. So, so if you want to think about it, all you got to do is look at these numbers and say that's roughly the percentage, roughly. Okay. So that means, we have of order 35% of our energy coming from petroleum, oil. Notice here there's biomass, for those of you that can read it. It's about 5%. That little biomass didn't show up on the slide 6 years ago, okay? We have coal, we have natural gas. This one, as everyone knows, is getting bigger, and which I'm a fan of, by the way. I'd like that to get bigger, this to get smaller. I realize that might be a little controversial in this part of the country, I guess, or at least in West Virginia. I don't know how much coal there is in Virginia, probably not so much. But if we think about it, if we think about the planet and not our own provincial sense of what we need to do, we really need to leave coal in the ground. I like to say that the best form of carbon sequestration is to leave coal in the ground. Okay. And so we have to find ways to transition those economies on the people so that they can certainly have good jobs, but not by harming the planet. And then we have geothermal, we have wind, we have hydro, we have nuclear, and we have solar. And the boxes up here are absolutely not to scale, because if you look up here, solar is 0.158. So that's less than 0.2% of our energy is coming from solar. That number, if you 5 years ago, it read 0.06, so it's doubled, but it's a doubling of a very small number. Okay, so those are the inputs. Over here are the uses. This is the demand. So the demand, if you notice down here, the big fat green thing here, which is oil, is mostly going into this box, which is transportation. Okay, so oil is we mostly use oil for fuels. Okay, to fuel our vehicles. We also use it in industrial processes. There's a small piece that goes into residential and commercial uses, but these are buildings, okay, and this is industry. Up here, so this is where the fuels are going. I don't want to take too much time on this slide, but I want you to see that up here this is for electricity generation, and you can see the big black one here is coal, okay, and so in fact, roughly, it used to be more than half was coming from coal. Now with natural gas prices going so low, In fact, the natural gas component is going up, which is, for the environment, is a good thing. And then you see there's a lot coming in from nuclear, some from hydro, and you can't even see the little yellow feed from solar, because it's just small. I mean, we talk about it a lot, but it's an incredibly small resource. Wind has also a small piece, 1%. The other important thing to look up over here is this. These numbers, this says energy services, which means that out of the 97 quadrillion BTUs that we use each year, 41.7 in 2011 were actually used to do useful work, okay, or for heat. The rest of it is what's called rejected energy. That's wasted heat. It's just staggering, the amount of heat that is lost, okay, that we could and potentially recover. So that's a really prime problem for figuring out, how we can do waste heat recovery. Is a really interesting problem. Okay, so the summary though is that as of 2011, this 82% of our energy is coming from 3 sources: from petroleum, from natural gas, and coal. And those are non-renewable fossil fuels that, if you look at the data, and I'm not talking climate models here, I'm talking about empirical measurements, it's clear that the burning of fossil fuels is producing CO2. The physics is very clear about absorption of sunlight, and re-emission is infrared, which warms the earth. So those fossil fuels are contributing to global warming. They clearly distort our international relations because of this box right here, okay, because of the amount of oil we need. I think we don't see the Middle East with as clear an eye as we would if we didn't need their oil. And they clearly threaten the global economy. Every time we've had huge spikes in the oil prices, the economy has problems. So wouldn't it be nice to live in a world where, in fact, our international relations could be decoupled from the energy issue? And I think, in fact, because of revolutions in horizontal drilling techniques in this country, there is tremendous evidence now that really things have changed. I now talk about it differently, because it's very likely that by 2020 we will be an oil exporter. We will be a natural gas exporter. That's the prediction now, which is really amazing. And it's because of revolutions in horizontal drilling techniques. The issue is whether we can do it safely and not harm the environment. But if we can, then really our international relations should in principle be decoupled. It never seems to be, but and our own personal, from a nationalistic perspective, our economy should be pretty safe. So then, one question that you ask is, I used to say, well, there's a triumvirate of reasons to work on the energy problem. But really, because of the revolutions that we've seen now in petroleum and natural gas recovery here at home, the U.S., if they want to be provincial about it, would now say that those are no longer compelling reasons to invest in alternative energy. And that is actually a little scary for me, because I think that we have to really pay attention to the problems that are coming about because of the burning of fossil fuels, because of the climate change that's happening as a result of that. And so I still view this as a compelling enough reason to really work on and try to help in the science aspects. I'm not a policy person, but the policy part and the economics part needs to also be worked on. Okay, so I want to lead you through energy, both how it exists today and also how I see it being tomorrow, and in terms of various aspects of it. Because basically, because of the climate change problem, we really need to be thinking and aggressively moving toward efficient use of energy. There are lots of things we can do that don't require any scientific input, even just turning off the light when you leave a room, okay? And then sustainable sources, because we actually have plenty of carbon in the ground. There's no question that if we wanted, we could keep burning it. But eventually, and so I don't even go to that argument. But I think it's much better to think about what can we do to move as scientists, as chemists. How can chemists help in moving us onto a way in which we can get sustainable sources that will go beyond when we run out of carbon. Okay. So we'll talk about that for electricity and fuels. The issue of storage is incredibly important because that's why solar and wind are not ever going to be a major part of our portfolio for electricity until we can actually store enough electricity from those intermittent sources to be able to use it, at night and when the wind doesn't blow. Very serious problem because storage, we just don't have good solutions there yet. So we'll talk about that a little bit. And transmission of electricity, there are issues associated with that as well that I don't think I'm going to have much to say about that right now. We can talk about that later. So as Ray mentioned, about now, I guess it's almost 6 years ago, after I read the executive summary of the Intergovernmental Panel on Climate Change report of 2007, I don't know, I woke up. Because I think the U.S. has been asleep for 30 years, basically since the last oil crisis. And I was asleep too, I fully admit it. But I thought, it's time for me to use the techniques that I've developed over the years and whatever my expertise is to try to help. And so what I did over the last 6 years is to move my research entirely, as Ray said, into problems that I hope will help get us off of fossil fuels. So I will say that before I woke up, I did have one project that was related. In fact, I guess in some sense this is what interested, or partly interested, the mechanical and aerospace engineers at Princeton in bringing me to Princeton, is I've done a lot of work on material science associated with turbine engines that are used both on airplanes and in power generation. I've worked on the heat shields that are involved in that. It doesn't sound like chemistry, but in fact, very interesting material science problems at the atomic scale. Not working in that anymore, but the idea there was to have ceramic heat shields that could last longer and operate at higher temperatures so that you could have greater, either they'd last longer or you would have greater power generation or thrust on airplanes. So that's an energy problem for sure. What I'm working on now though is, and I'll have one slide to talk about this, is combustion of biofuels. And so I'm just going to run through these and I'll tell you more about it as we go. This is a mock-up of ITER, which is the International Thermonuclear Experimental Reactor that's being built in Europe. It's a fusion experiment. Princeton lives right across the street, well, right across the Route 1 from the Princeton Plasma Physics Lab, which is one of the premier places for magnetic confinement fusion. And the engineering school works closely with that lab. And it turns out that a lot of the issues there now are not so much the plasma science, which they've been working on for decades, but are material science problems, which is something that I work on. And so I'll have something to say about that as well. Ray mentioned I also work on structural materials, for example, lightweight alloys that could be used to lighten the weight of vehicles, photovoltaics, photoelectrochemical cells, something which Ray is working on as well, which is essentially a way of taking sunlight. I'll have something to say about this, and trying to take sunlight, water, and CO2 and run combustion backwards to create a fuel or a fuel precursor, in this case methanol. If you have methanol, you can actually convert methanol, as many of you know, through the mobile process to gasoline, and so using zeolites catalysts. So that's a very important problem. And then also, once you have the fuel, that you could think about that as a way of storing the energy of sunlight, by the way, then you could imagine also running that fuel through a fuel cell to generate electricity when you need it. And so I actually am also in a collaborative project to work on solid oxide fuel cells, which they're out there commercially, but they have a huge amount of durability problems, and that's something that we're trying to help resolve by figuring out how to run the reactions at lower temperatures so they'll survive longer. So that's my portfolio of research projects, more or less. So that's not me, but I wish it was. So this is my slide that talks about the way I think about how I go about doing research. So basically my research starts with the very fundamental laws of physics that describe the distribution of electrons in matter. And what I mean by that is both their spatial distribution, so how they're spread out in space, but also their energy distribution. Both things are important. And they're both determined by quantum mechanics. That's the governing equation is given right here. It's the one equation that's going to be in the entire talk. And it's a very famous equation called the Schrödinger equation. And it's a wave equation that describes the electron distribution in space through this function here, which is called a wave function. This Greek letter psi of r means it's the value of the function in space. It tells me the probability of finding the electron somewhere in space. And E is for energy, okay? And we all learned in science that total energy is divided into kinetic and potential energy. So there's a kinetic energy term and there's a potential energy term, and they're summed together to give you the total energy. And that equation is a beautiful equation, except it's basically useless. The reason it's useless is because you can only solve it exactly for one electron. So that means if the world was made of a hydrogen atom and only one of them, I'd be fine. But life is much more complicated than that, as we all know. And so you have to find approximations to this Schrödinger equation that still retain and capture the faithfulness of the physical interactions, but in fact are approximations that are solvable. So what we do is to write down use pencil and paper to write down some equations that then we transfer to a computer code that then we run on a computer, a big supercomputer, and then out comes some information. I'm going to describe this information later, but the bottom line is this little donut here is telling me where an electron is in this solid, and this set of graphs here is telling me the energy of that electron at different points in this solid. Okay, and that's the kind of information I can get out, and I can then use that to understand physical observables that someone can measure, and that's what I do. Okay, and what my group does. So let's go back to thinking about energy, and so if we think about electricity and fuels today. As I said already, they're mostly fossil carbon based. This is coal, this is petroleum, oil, this is natural gas, these are tar sands. And so the question is, what about, what could we possibly replace at least oil with? What could we think about? And so a lot of people talk about biofuels, really daunting task, okay? In terms of the infrastructure, in terms of whether it's actually worth it, in terms of whether or not you actually make it CO2 neutral. It's not obvious at all that it's CO2 neutral, especially in the case of ethanol, which is miscible with water, and then you have to do a distillation. I mean, it's just ridiculous. Okay, so there are lots of problems. I'm not saying it's impossible. It would be really interesting if you could develop a membrane that would be permeable to ethanol and not permeable to water. If you did that and you didn't use energy, and there are people working on that, I don't work on that, but if you did that, you might have a way of making a process that involved ethanol, such as corn here, or cellulosic ethanol, worthwhile. But as it currently stands, it's really quite problematic. I'm also bothered by the fact that we're using a food for for energy. I think that we really shouldn't be doing that, and so I have a big X through that, and that's my own opinion. There's a lot of interest in using biomass waste. I think that's fine. If you know that there's some waste around that isn't actually being used, those are wasted carbon atoms. I'm all in favor of using carbon atoms in a good way, okay? So if you can do that, if you can take corn stover and other parts of corn that wouldn't be used for anything else by the farmer, which isn't completely obvious, then I think it would be worthwhile. And this is basically parts of forests, and I have problems with that. I mean, if you think about it, there really isn't that much biomass waste. There's big arguments about it, but in fact, a lot of biomass is used to make paper, is used to make plywood, other things. There are lots of uses for it, and it's not obvious we actually have a lot of it lying around unused. So, and I don't like the idea of using land that's arable land that should be used to grow food for the unfortunately growing world population to take care of our energy problem. So what I'd rather see is that we figured out ways to use desert plants or algae that was used that could grow in brackish water so that you wouldn't be using fresh water. Because another real problem that we face, and is really important to study, is the competition between energy and water. Every single, a power plant uses lots of cooling water. You need water to basically keep the solar cells clean. I mean, there's all sorts of cases where you look and you see there's competition for use of water, and water is of course a very important resource that we don't value yet as much as we will in the future for sure. So my hope is that we'll be developing fuels from these. The nice thing about algae is that it actually produces essentially a hydrocarbon. It produces a fatty acid, okay? And the cool thing about it then is that you can do a transesterification of that to essentially make what's referred to now as biodiesel. You probably all heard about biodiesel. And it's a long hydrocarbon chain with an ester group on the end. So for the chemists in the audience, okay? And so it actually is a very energy-dense fuel. It turns out that the hydrocarbon chain is really too long. I have a picture of it, yeah, right here. So, so for those of you that aren't chemists in the audience, every vertex is a carbon atom. And so the bottom line is you have a lot of carbon atoms here. And so it turns out you can't use the biodiesel fuel by itself because, well, you might be able to near the equator, okay? But if you live in Minnesota and you put the biodiesel fuel into your gas tank, you're going to have a solidified fuel, you know, in the winter. So it has to be used as a blend. So one of the things that's going on at Princeton, we lead the only combustion science energy frontier research center for the DOE, for the Department of Energy. And this is actually data from my colleague, Ed Law, who's the director of the center. And this is a very cool experiment, okay? So this is actually what hexane looks like when it's burned. And it's very, very clean, okay? Sorry, yeah, hexane or hexadecane, I'm not sure. Anyway, it's a pure hydrocarbon that's basically a gasoline mimic. This is pure diesel, and you can see, in fact, then what's down here are coffee filters in which he's collected, very, very low-tech experiment, coffee filters that have collected the soot. Notice the amount of soot here. That's normal diesel, okay? You've all experienced being behind a diesel truck or maybe been to Europe and you know what it's like. And what's shown here in these other cases are blends of biodiesel into the normal diesel, showing that, in fact, you get much cleaner burning as you blend in. Okay, and so this is the pure biodiesel. You can't use this, but this is 10% and I think this is 20%. And the amount that you blend in means you're using that much less of a fossil fuel. So that's a good thing. And this is the kind of thing that we're trying to understand. What I'm doing in this regard is we have developed quantum mechanics methods that can describe accurately the combustion chemistry of molecules of this size, which is unusual to be able to do that. And so we're trying to figure out the actual chemical reactions associated with how those things burn. Okay. Now I mentioned solar panels, wind. You know, we're already there. We've got lots of that, but we don't have it at grid scale. That's what I was showing you. By grid scale, I mean really, you know, taking over from coal. What are the challenges? Well, I mean, you may know that there's been a real revolution in, well, a drop in the price of solar panels. And that has been because China actually dumped a lot of solar panels on the market and the price crashed. And a lot of people were upset about that. I actually was not upset about it because I think we want mass production to drive down the cost curve so that we can actually, you know, at some point reach parity. It's not going to solve the problem. We still need storage because otherwise you can't use these at night, right? But nevertheless, there are other issues that you have to think about. It's not just about cost. This is a picture of molten silicon. It costs a tremendous amount of energy, in fact, to make these solar cells. So we have to start thinking in chemistry communities about doing what's called life cycle analysis, where you actually take into account from the very beginning how much energy does it take for you to prepare the starting materials and manufacture it until all the way through end of use. And that's how you have to make some decisions about whether you want to go with ultra pure silicon, which is what's required right now with standard solar cells, is really ultra pure silicon. We'll talk more about that. The issue with wind turbines right now is that they require in their motors, you may have read about this, they require rare earths, okay, rare earth elements for the magnets, for the permanent magnets. And so that's also a really interesting challenge. I don't work on it, but again, very interesting science challenge. How do you replace rare earths and still get a magnet that's a permanent magnet that can be used in the motors? And the problem there is really, in some sense, a national security issue because China controls 97% of the mines for these. And that's partially an economic issue. We had a mine in California that didn't make it economically and it's now being reopened because the price has been driven up. So there's very interesting trade-offs that we can think about there too. But long term, I think these will continue to play a role, especially if we can make these cheaper from different materials that don't involve this kind of expenditure of energy. Another, I think, really important area to not drop off the palette of solutions is fusion. And so that's the fusion reactor here. What I'm showing here is the problem with these two, which I already mentioned, which is the intermittency of power versus time. So if the sun isn't shining, you don't get any electricity. If the wind isn't blowing, you don't get any electricity. It's really a challenge. The problem with the fusion reactor is that we have materials issues associated with the fact that the fusion plasma is contained in this model. It's like you're trying to contain a mini sun, okay? Inside a magnetic field. And it mostly works, but it leaks, okay? So when it leaks out neutrons, which basically end up destroying any solid, because the neutrons will go into the solid, they knock atoms out of place, and then that, along with the deuterium and tritium that will come out of the plasma, ends up embrittling the material. And so in fact, this is something that I did a little bit of work on for the Princeton Plasma Physics Lab. One of the materials they really were planning to use, and in some sense are still planning to use it in this particular experiment, is tungsten, okay, tungsten. And so tungsten is interesting. If you think about your incandescent light bulb, the filament is made of tungsten. So it can withstand very high temperatures, which is important if it's next to a sun. I mean, not obviously, I'm being a little facetious. It's not like it's next to the sun, okay? But it can withstand very high temperatures. It's a very good neutron absorber, has very high thermal conductivity. These are all really important properties. There are some other ones as well. But it wasn't really known in terms of hydrogen isotopes how those hydrogen isotopes would behave as they come out of the plasma and interact with the tungsten surface. And so we did quantum mechanical calculations to look at understanding what happens when a neutron comes in and knocks out an atom out of the solid. What happens when that so-called vacancy is present? And it turns out if you don't have that vacancy, if there's no neutrons, then the deuterium and tritium don't want to go into the material at all. It's just not, it's way uphill energetically. Once you've created this little bubble, it sucks up deuterium and tritium. It's amazing. And as a result, you end up embrittling the material. And so that was an important thing for them to understand because what that does then is lead to fracture. So it means we have to think of another solution. And so the next phase of my work in conjunction with the Princeton Plasma Physics Lab is in fact to work with them. They are developing, this sounds crazy if you're a chemist, you go, what? This is a liquid lithium wall. Okay, now how would that work? Well, it's kind of like, you see these fountains that have a film of water that come down them. So the idea is for capillary forces to have a liquid, very thin layer of flowing lithium. Why lithium? Because it's a good neutron absorber. Why a liquid? And it doesn't affect the plasma because it's low mass. Why liquid? It's just a beautiful idea. The point is that if you have a solid and you knock these atoms out of place, then there's a place for the deuterium and tritium to go in. You have a liquid. The liquid is already disordered, and it doesn't care about the neutrons. So it's beautiful because it can't actually affect the neutrons. Don't do any damage. They can't do any damage to a liquid. So this is being tried experimentally, and we have done now simulations of liquid lithium using another technique that we've developed that essentially goes from that wave function based approach of quantum mechanics to one that just relies on the electron density. So the density, so the electrons per unit volume, okay? And by doing so, the calculation is much cheaper, and so we can actually simulate the behavior of liquid lithium. And we're starting now to look at the surfaces of liquid lithium, and eventually we'll look at how deuterium and tritium either get incorporated or not in the liquid lithium. Very hard to do experimentally, so it's a role for computer simulations to try to figure that out. So that's one area that we're currently working on. So I mentioned solar energy. I mean, everybody talks about it. You know, there's so much energy from the sun, can last forever. It's really great. It's a question. Problem is that sunlight is diffuse, and to get it and convert it into something useful is not trivial. So the goal is you have sunlight, you have some magic material, a magic box that somehow converts the energy from sunlight into electrons or electricity, or into doing chemistry, making a fuel. Okay, so how's that going to work? Well, this is a little tutorial of how a photovoltaic works. So I mentioned that electrons, what I calculate, what I'm interested in is not only where the electrons are in space, but what their energy is. Okay, we calculate their energy. In what's called a semiconductor, like silicon, which is what these photovoltaics are typically made of, the photovoltaic that so photo, light, voltaic, meaning electrons. What it does, so this is now showing an energy distribution, okay, a schematic of the energy distribution of a semiconductor. So you have this block of electrons that have a whole set of energies in what's called the valence band. It's where the valence electrons are, okay? And then there's a whole bunch of empty states initially. They're just energies that if I'd solved the Schrodinger equation, I would have found those energies, but they're so high in energy that the electrons don't live there, okay? The electrons live down here initially, but then if I come in with sunlight, then what happens is it creates a situation where an electron can get excited up to this conduction band. Why is it called the conduction band? Because the electrons are very weakly held at that energy. They have so much energy that they can almost easily flow, just like in a copper wire. They can conduct at that energy. They're not so strongly held to the atoms that they came from. So and what happens is that electron is living now at this energy in the conduction band, and what's left behind is effectively a positive charge. It's called a hole, okay? And that absence of an electron lives at that energy, so it creates what's called an electron-hole pair. And what's key to making electricity from sunlight is the separation of that electron and hole, okay, so that they move out and to an external circuit so that the electron then can be used for useful work. That's how it works. And what you see here, there's this metric that's called the band gap. It's the forbidden energies. You solve that Schrodinger equation, you find that there is no way that an electron in a semiconductor can have an energy in this region. It's really critical because the energy of this photon, of the light, has to be at least as big as this forbidden gap so that the electron from down here can move up here. Okay? So you have to have a photon energy that's greater than the band gap. And it turns out that you can show through thermodynamic arguments that the maximum power is obtained when you have a semiconductor that absorbs visible light, okay? And that's actually really good because if you look at the sun, the sun is yellow. That's visible light. That's the peak in the solar energy spectrum. So it's good that that's what you need because that's the sunlight, that's where the peak is in terms of where most of the photons are in their energy. And then I say no traps because these electrons can get trapped. If there are impurities, that's why you need ultra-pure silicon. You have to have You can't have places, defects in the material where the electron just gets stuck. Really important. So it makes it very expensive. So that's a problem that we're working on. I'm going to show you a few examples of that. Another issue is in the future, we want to be able, as I mentioned, to take the energy of sunlight, carbon dioxide, water. You know that when you burn a fuel, that's what you make. You make carbon dioxide and water. Unfortunately, we also make soot and you know, NOx and stuff like that that are not good for you. But in principle, if you did really perfect combustion, you'd get CO2 and water and nothing else. And what we want to do is run that reaction backwards. Take the CO2 and water and make sunlight. And we want to do that, for example, in a photoelectrochemical cell where now we have two of these semiconductors. We have a valence band here, conduction band here, valence band here, conduction band here. Turns out when they're immersed in a liquid, the band edges shown here actually bend in certain directions. And so that's beyond the scope of this talk. But the sunlight comes in, you make an electron-hole pair, hopefully at the anode, and that, it turns out then this hole drifts up in energy. Remember, this is an energy diagram. And that hole is a positive charge, and it really wants to be neutralized. And so what happens is, it can, in principle, strip electrons off of water and make oxygen. That's what plants do, okay? Plants take in water, and they make oxygen as a byproduct. They don't really want the oxygen. We're lucky that they don't want the oxygen, right? The cathode, on the other hand, light comes in potentially for a semiconductor, you make an electron-hole pair, and now it's the electron that's going to drift down in energy, and it comes down here, and that electron can be used to, in fact, reduce carbon dioxide. It's been shown actually in the laboratory at Princeton, in Andy Picarsley's lab at Princeton in the chemistry department, that you can, under certain circumstances, take electrons and protons from an acidified solution and convert CO2 to methanol, as I said before. So that's something we're also working on. We need really cheap, we need efficient, so this sounds great, right? Andy's already solved our problem for us. Why aren't we making gasoline from this? Because it's very inefficient. So we still need to figure out ways, we need to understand the mechanism, as chemists love to do, but and hopefully that's going to teach us something about what's necessary in order to make the materials better, the catalysts better, so that it can be done efficiently and selectively. So we need efficient, robust, cheap electrode and catalyst materials, and that's something that we're working on. And I'll just give you, so what this says, it requires the electron energy and the hole energy to basically straddle the free energy of the reaction. And so that's actually shown here. Here's another picture of that valence band and conduction band, and a cartoon of a photon coming in and an electron being excited. And the electron has to live at an energy that's higher than the energy to undergo these reactions to take CO2 to methanol. Or in this case, for the hole has to live down here so that it has the proper energy placing to be able to oxidize water to make O2. Okay? And so that requires looking at a bunch of semiconductors and seeing which ones have the right energies, the right band edges. So one of the things I did was to think about, well, what does nature do? It doesn't always work to do this, but I thought it would be interesting to think about it. If you go look at photosynthesis, what you find is that the center that oxidizes water and creates oxygen in photosystem 2 actually has this really cool little cube in it that's made up of manganese and oxygen and calcium. So if you translate that into just a solid, which is what I was interested in, an electrode material, we thought of looking at manganese oxide, okay, which is actually a rock salt structure. And it turns out that the band edges, the conduction band edges here and the valence band edges are placed properly, but it only absorbs ultraviolet light. The band gap is too big. Why is that a problem? Because if you are thinking about shining sunlight on it, only about 2 or 3% of the sunlight is UV or higher. Okay, so you've immediately said your upper bound on efficiency is 2 or 3% because you're throwing away all the rest of the light. That's useless. You want to have this visible light. So we asked the question, could we alloy it with something that might change the band gap to be acceptable? And so it turns out that we developed a scheme for calculating these band edges on an absolute scale, and showed that you could alloy manganese with zinc, which is isoelectronic in some sense with calcium. And it's interesting because you can get the band gap down into the visible. Anything below about 3 eV is in the visible, and still keep these band edges above in the right placement so that you could do water oxidation or reduction of CO2. So that's the kind of thing we like to do, is play with these materials to find out how we can adjust their properties to improve the efficiency. I also mentioned that it's really important to think about whether or not you make traps, and one of the things that you want to avoid making these traps. Turns out that the semiconductors, both in the photovoltaic application and also in the photoelectrochemical cell that I showed you for either oxidizing water or for making fuel, or making fuel precursor like methanol, you have to dope them. And what that means is you do some substitution of an element into the lattice of the material. And what this is showing, so we started looking at hematite, Fe2O3. For those of you that prefer, you can call that rust, okay? Because that's effectively what it is. This is a picture showing what's called the photoconductivity as a function of applied potential. Doesn't matter really what this means, except photoconductivity means I shine light, electrons came out, I like that, okay? And so if it's big, I'm happy. And what you see up here is that I got the biggest response from silicon and the worst response from titanium. They're both group 4-like elements. The question is why? So we did calculations. This is going and showing you, a little bit of what we did. I said when I introduced the methods, I showed you a picture like this. What this is showing you is what the electron energy is in hematite that's going through the solid. And what the electron energy is when it lives on an iron versus when it lives on a titanium. And what you can see, you can think about this as if you're walking along and you hit a pothole, like we have many in New Jersey, okay? And you get stuck, okay? So it's a trap. This is a trap. So what this showed is that the electron loves to be on titanium. It's lower in energy. That's a trap. A huge trap, actually, because this is in electron volt, so it's a large trap. So that explains this data, okay? And this is the picture I showed you before when I introduced our methods. This is for silicon. Very cool that it turns out we predicted that it's completely reversed, okay? Going from titanium to silicon in the doping in the lattice, the electron prefers to stay on iron. It will never live on silicon. Okay, because this is the energy on silicon, it's much higher in energy. And that, if you go look at what the electrons are doing, that's this distribution of this extra electron. It turns out that silicon just adds electrons to the lattice, which helps the conductivity. That's what it does. And it doesn't trap. And why it doesn't trap. So one thing I teach my students at all times is I say it's really important that you don't just generate a number. You got to understand what it means. You have to understand the rationale, otherwise you don't learn anything. And so what's really interesting is to think about why it's flipped. And the reason it's flipped is because silicon oxygen bonds are much more covalent than titanium oxygen bonds. And as a result, that extra electron I've added actually has to go into an anti-bonding orbital. For the chemists in the audience, you know what I mean by that. And that is what raises the energy here. And you don't have that same response here. So we understand why silicon is good and why titanium is bad. And so it turns out we can say that you can increase the electron conductivity by doping with a covalent oxide. That's sort of a design principle that comes out of this work. And so that should increase the number of electrons, the charge carriers, without trapping. So that's the kind of thing that we try to do. I think you want me to stop soon, right? Yeah? Okay. So I'm just going to, this is more data than is important, but we also look at water oxidation. We looked at water oxidation on hematite. Don't worry about the details. What's really interesting, though, is that This is what's called, catalytic chemists will recognize this as a volcano curve. Don't ask me why it's called a volcano curve, but it is. And whatever is high up here means that you should have the most active catalyst. And what we have shown is, well, what we had predicted is that nickel dopants in the lattice should be the best. And after we did this work, but before, unfortunately slightly before this got published, a paper just a few months earlier got published, which provided experimental verification of that. So that's very cool, okay? So that's the kind of thing that we do, and I don't have time to tell you what the reasons why we predicted that, but we understand why it lowers the barrier for this reaction. So, so I think that I will skip this. I was going to tell you a little bit about fuel cells, and I will just move to spend a couple minutes about the Almoner Center. Okay, so this is a center that this is my mission statement. Okay, that we want to provide both technical, policy, and economic solutions within the center to preserve the planet for future generations. I mean, that's all. That's all we want to do. Okay, it's why I don't sleep very much. Because I feel so strongly about this, and that I want to do my part to really ensure the preservation of the planet. And it's bringing together, it's housed in, administratively, it's housed in the School of Engineering. The donor, Gary Andlinger, said the director must be a professor of engineering. And I am a professor of engineering, but also I guess in some sense I'm an interloper because I'm a physical chemist by training, but I am a professor of engineering. We are working closely with the School of Architecture. In fact, we're doing a search right now for a joint faculty member looking at green building design and also urban design. Work closely with the scientists. Also working closely with people that are interested in energy economics, energy policy, environmental economics. And I have been recruiting people. We have experts in the Woodrow Wilson School of Public and International Affairs at Princeton who work on the psychology of human behavior and about behavior and decision making. And that's clearly a very important piece of this because you need society to adopt these new technologies, and we have to figure out ways to do it in such a way that people don't feel their quality of life is being compromised. Otherwise, they're not going to do it. Not going to adopt them. So it's really involving all these areas, reaching out across the whole campus. And the next slide is a slide that I was asked by one of the trustees of Princeton. He asked about the center, and I was talking to him, and he said, you should make a slide of that. So he said, what's your vision? What's your vision for the in terms of energy? I said, well, I don't think about energy for the next 5 years. I'm really thinking about the entire 21st century at a minimum, because it's we're not going to solve these problems on one time scale. We're going to have certain things we're going to do right now that we can do in the next 10 years. Then there's some other things over the next 25 years, and then over the next 50 years, okay, at least. And so that's what this picture is, and it's what I think I will end with, which is to say that there are lots of boxes here. A lot of these things we're already doing. So I view this, notice the axis down here. It says time, near term, medium term, long term. Conveniently, there are no numbers. And that's on purpose because I'm not a wizard. I can't predict exactly when we're going to be able to do all these things. But these are all the things that, at least as of now, that I think of as key to solving the problem. No one technology, no one technology and no one policy are going to solve the problem. It's going to be a portfolio. We're already doing hydrofracking of natural gas. It's already displacing coal because of the economics of it. That's a good thing from the environmental point of view. The clean is still an issue, right? And so there are still issues there in terms of research that has to be done, both in terms of the wastewater and in terms of methane emissions. Turns out that leakage from those wells is a significant problem because methane is an even worse greenhouse gas than carbon dioxide. Everybody concentrates on carbon dioxide, but methane is actually worse. So we could be shooting ourselves in the foot if we don't do that right. Electric vehicles we already have, you know. But there's, of course, there's work to do in terms of batteries. But I think this is really a big area, is energy efficiency in the short term. There are so many things we could do that already exist that don't require R&D, and we should be doing them. Many countries are. We have to get on the bandwagon as well. And there's still more to do in terms of you know, in terms of research there. Intermediate term, you know, I personally think we are going to have to go forward with more nuclear power plants for a while, unless natural gas can actually provide all of the electricity. It could be that we could do okay there. We need more our grid system. I mean, you guys also have experienced problems with your grid down here. Yes, I'm pretty sure in serious storms, right, with power outages. The grid in the Northeast is just amazingly fragile. But it's really, it's a huge problem in terms of the entire infrastructure of the United States. We really need, I think we need to think like modern day Eisenhower's, okay? Eisenhower built, you know, had the vision of the interstate highway system, and we need that kind of leadership to build that kind of approach to how we transmit electricity. Because in fact, if you look at where wind is generated, it's mostly in the middle of the country, and we have to push it out to where the people live. And the people live on the coasts, mostly. And so there's a whole issue associated, and the same thing with solar, is mostly in the southwest, right, is the greatest resource, and that has to be pushed out. So there's many areas where there's a great need. I could talk forever, so I should stop. And just say that, you know, long term, I hope we get our fuels from sunlight, CO2, and water. We're a long way from that, but I really hope we are. We need the grid scale storage for wind and photovoltaics and solar thermal to really penetrate. Ultimately, electricity from fusion power, I believe, should be the answer. And then there's all sorts of issues about the environment and about water that we could also talk about. So with that, you know, I hope we will see a future which looks quite different, and I need to thank my research group and various sources of funding and you for your attention.